The Carnot cycle represents an ideal heat engine that operates with the maximum possible efficiency between two thermal reservoirs. Although it cannot be perfectly realized in practice, it provides a fundamental benchmark for all real heat engines. In this video, we will explain what the Carnot cycle is, the four processes that define it on PV diagram and TS diagrams, and why it is so important in thermodynamics. First, what is the Carnot cycle? The Carnot cycle is a reversible thermodynamic cycle that operates between a high-temperature reservoir, TH, and a low-temperature reservoir, TL. It was introduced by Sadi Carnot in 1824 and is based on the assumption that no energy is lost due to friction, heat leakage, or irreversibility. Because of this, the Carnot cycle defines the maximum theoretical efficiency any heat engine can achieve. The four processes of the Carnot cycle. The Carnot cycle consists of four reversible processes involving an ideal gas as the working fluid. 1. Isothermal expansion at high temperature TH. The gas is in contact with the hot reservoir expands isothermally, meaning the temperature remains constant. The heat, QH, is absorbed from the hot reservoir. The gas does work on the surroundings. Because the temperature is constant, all the absorbed heat is converted into work. On the PV diagram, the process appears as a downward-sloping isothermal curve. As volume increases, pressure decreases. The area under this curve represents the work done by the gas. Since the temperature is constant, internal energy remains unchanged. On the TS diagram, the process is represented by a horizontal line. Entropy increases. The area under the curve represents the heat absorbed from the hot reservoir. 2. Adiabatic expansion. The system is thermally insulated. No heat is exchanged with the surroundings. The gas continues to expand and do work. As a result, the temperature decreases from TH to TL. This process connects the high-temperature isotherm to the low-temperature isotherm. On PV diagram, the curve is steeper than the isothermal expansion. Pressure drops rapidly as volume increases. No heat transfer occurs during this process. On TS diagram, the process is shown as a vertical line downward. Entropy remains constant. Temperature decreases. This is why adiabatic processes are also called isentropic processes in ideal conditions. 3. Isothermal compression at low temperature. The gas is placed in contact with the cold reservoir compressed isothermally, meaning the heat, QL, is rejected to the cold reservoir. Work is done on the gas. The temperature remains constant during this process. On PV diagram, the process follows another isothermal curve, but at a lower temperature. Volume decreases while pressure increases. Work is done on the gas. On TS diagram, the process appears as a horizontal line at temperature TL. The entropy decreases. The area under the curve corresponds to the heat rejected to the cold reservoir. 4. Adiabatic compression. The system is again insulated. The gas is compressed without heat transfer. The temperature rises from TL back to TH. This completes the cycle and returns the system to its initial state. On PV diagram, the curve is again steeper than the isothermal curve. Volume decreases and pressure rises sharply. No heat is exchanged. On TS diagram, the process is represented by a vertical line upward. Entropy remains constant. Temperature increases from TL back to TH. This process closes the cycle and restores the system to its initial state. Overall shape of the Carnot cycle. On the PV diagram, the Carnot cycle appears as a closed loop bounded by two isotherms and two adiabats. The enclosed area represents the net work output of the cycle. On the TS diagram, the cycle forms a perfect rectangle. The rectangular area on the TS diagram represents the net heat converted into work. Finally, the Carnot efficiency. The efficiency of a Carnot engine depends only on the temperatures of the two reservoirs. The Carnot efficiency is 1 minus TL divided by TH. TH is the absolute temperature of the hot reservoir. TL is the absolute temperature of the cold reservoir. Important note: temperatures must be in Kelvin. Increasing efficiency requires increasing TH or decreasing TL. Why is the Carnot cycle important? Even though it is an idealized model, the Carnot cycle is extremely important because it sets the upper limit for heat engine efficiency. It helps engineers evaluate real engines. It forms the foundation of the second law of thermodynamics. Any real engine will always have an efficiency lower than the Carnot efficiency due to irreversibilities. Thank you for watching. See you soon.